All right, hello there. Today we're going to look at one of the special cases of factoring. It's called a difference of squares. That's exactly what it says. It's a difference, must be a difference, and it has to be squares. A difference of squares is always a binomial, two terms, always a binomial, two terms. And it must be a difference. There must be a subtraction between them. If it's an addition, it doesn't apply. Both terms must be perfect squares. You know what a perfect square is. And we're always going to look for a GCF first. So sometimes they won't be perfect squares, but the GCF will make them perfect squares. Other times they'll be perfect squares, but they'll still have a GCF that we'll do first. And when you factor it, you're going to make your two binomials. And what you're going to do is you're going to take the square root of each term, and then the binomials are going to just have opposite signs. So for instance, x squared, that's a perfect square. Y squared, perfect square. Minus, it's a difference. So do the square root of x squared, that's just x. And do the square root of y squared, that's just y. You'll always get a plus and a minus every single time. If you want to put the minus first and the plus second, that's fine too. These are pretty easy. I'm going to do a bunch of them, but I'm going to try to do them quickly. So here we go. Here's our first four. K squared minus 100. K squared is a perfect square. 100 is a perfect square. We have a difference. We're ready to factor. There is no GCF, so I do the square root of k squared. That'll just be k and k. I do the square root of 100. That's 10 and 10. And I have to have opposite signs in my parentheses. One's a plus, one's a minus. The reason why you just get a binomial, and you probably remember multiplying these with FOIL, the outer product and the inner product are opposites and they cancel out. That's why you just get a binomial. Pretty simple. 81 minus r squared. Both perfect squares. We have a difference, no GCF. So I'll do the square root of 81. That's 9 and 9. The square root of r squared. That's r and r. One parenthesis gets a plus. One parenthesis gets a minus. Notice that with the r in the second position, it didn't change anything. It just changed method. Instead of r plus 9, it's 9 plus r. Instead of r minus 9, it's 9 minus r. 36g squared minus 49. We have a difference. Both are perfect squares. Take each square root. Square root of 36. Oh, sorry. And there's no GCF between 16 and 40, or 36 and 49, right? Okay. Square root of 36 is 6 and g. 6 and g. Square root of 49 is 7 and 7. I get opposite signs. One's a plus, one's a minus. I always put the plus first. There is a reason. We'll talk about that reason later. I always put the plus first. 16p squared minus 36. It's a difference. They're both perfect square numbers, but they have a GCF. And that GCF is 4. So even though they're perfect squares, we're going to do the GCF first. If you have perfect squares and they have a GCF, you will still end up with perfect squares. 4p squared minus 9 when I take that GCF out. Oh, so this 4 stays here. And now I do the square root of 4p squared, 2p. And the square root of 9, which is 3. And one gets a plus, and one gets a minus. So far, so good. Here's another set. 4x squared plus 25. I have a perfect square. A perfect square? I have a plus. This is not a difference. This is a sum of two squares. Guess what? I cannot factor this at all. This is prime. If you have a sum, you cannot factor it. Do not try to factor it if you have a sum of squares. It cannot be factored. The only thing could possibly be done is if these two numbers had a GCF, which they don't. So this is prime. Perfect square? Perfect square? Look, a second variable. That's okay. It's a difference. These two numbers have no GCF. So the square root of 11, or square root of 121 m squared is 11m. And the square root of 144 p squared is 12p. And one parentheses gets a plus, one parenthesis gets a minus, and I'm done. 45q cubed minus 20q. No perfect squares. But there is a GCF. The GCF of 45 and 20 is 5. And the GCF of q cubed and q is q. Well, watch what happens when I divide that GCF out. I get 9q squared. That's a perfect square now. Minus 4. That's a perfect square now. So now I'm able to factor that difference of squares that's left over. The 5q stays on the outside. The square root of 9q squared is 3q. 3q. The square root of 4 is 2. 2. 1 gets a plus, and 1 gets a minus. 100b cubed minus 36b. These are both perfect squares, but they have a GCF. The GCF is 4. And b cubed and b is GCF of b. So when I factor that out, it leaves me still a perfect square, 25b squared, minus still a perfect square, 9. All right, bring down the 4b, take the square root of 25b squared, it's 5b, and 5b, take the square root of 9, 3, and 3, one's a plus, one's a minus, and we're golden. All right, not too bad. We can also apply it to equations. Just want to show you 2 of those. Nice thing about solving equations is you're going to like the zero product property. First of all, you know it has to equal 0. This doesn't. So I got to subtract 81. So now my equation will say 4y squared minus 81 equals 0. Now that it equals 0, I can factor. I have a perfect square. I have a perfect square. I have a difference. I have no GCF. All right, 2 parentheses. Square root of 4y squared is 2y. Square root of 81 is 9. 1 gets a plus. 1 gets a minus. It equals 0. Now I'll apply my zero product property. One of these binomials has to be 0. Well, they're total opposites. That means I don't really need to solve them both. Whatever I solve for one, the other one is just the opposite. So I'll just solve this one. 2y plus 9 equals 0. Subtract 9, divide by 2. I get y is equal to negative 9 over 2. That means for this one, I'll get positive 9 over 2. So now that means my answer is y is equal to, let's see if you remember the symbol for positive and negative, same number. Remember that symbol, plus minus 9 over 2. One more. Got to make it equal 0 first. Subtract 48h. So 27h cubed minus 48h is equal to 0. I have a difference, but neither of these are perfect squares, but they have a GCF. GCF of 27 and 48 would be 3, and h cubed and h is an h. That leaves me 9h squared minus 16. And now check it out, both perfect squares. And look at my GCF. My GCF is a 3h. I have a variable in my GCF. That means that's going to be an option for my answer. So 3h comes along. I'll factor these two binomials. The square root of 9h squared is 3h again. And the square root of 16 is 4. 1 gets a plus, 1 gets a minus, equals 0. I have 3 factors that could be 0. And this 3h has an option. If 3h is 0, that means that h is equal to 0. Now these two are just going to be opposites. This time I'll solve this one. So if 3h minus 4 is equal to 0, add 4, divide by this terribly drawn 3, add 4, divide by 3, so h would equal 4 thirds. That means that this one will be negative 4 thirds. So my final answer is h is equal to positive or negative 4 thirds and 0. Difference of squares, not too bad. Have fun today.